Hi, in this video we look at Newton's second law, which is a quantification of the first law. If you recall, Newton's first law states that in order for an object to accelerate, this requires that the net force acting on that object not be equal to zero. In other words, there must be some net force acting on that object. What Newton's second law does is tell us, well, how much force we need for a given acceleration. So we could start off by saying that Newton's second law simply states that the acceleration is going to be proportional to the net force. That means that this ratio is a constant. The net force, the ratio of the net force to the acceleration, that ratio is a constant. So let's suppose we have a net force whose magnitude, so we have a net force and whose magnitude is, let's say, 12 newtons, and we're getting an acceleration whose magnitude is, let's say, 6 meters per second squared. If we were to change this from 12 to, let's say, 36 by tripling it, well, then the acceleration would also triple from 6 to 18, because the acceleration is proportional to the net force. If we triple the net force, we have to triple the acceleration. Now, you all know that all proportionalities can be expressed as an equality by multiplying, in this case, some constant times the net force. Question is, what is that constant? And the constant is the reciprocal of the mass. So we can say that the acceleration is going to be equal to the net force divided by the mass. Now, some books prefer to give this equation a little bit differently, and we can do that also. We can say that the net force, by the way, remember this little sign here means summation. It means the sum of all the forces. So the net force, that's the sum of all the forces, is going to be equal to the mass times the acceleration. There is another very important thing that needs to be pointed out here. What we have here is a vector. The sum of all these vectors is a vector. The net force is a vector. Some books, instead of writing this, they simply write this. So the net force, this is a vector, is equal to some scalar times a vector, which means that these vectors have the same direction. So the net force is proportional to the acceleration and acts in the same direction as the acceleration. To help us better understand this, we'll use this applet made by the good people at Colorado, the University of Colorado, Boulder. So, excellent website, really great applets that allow you to better understand the various phenomena that you might encounter in the course of your studies. So what we have here is a crate, and we have some forces acting on that crate. This guy here is exerting a force to the right, and we have the push of the floor upward on the crate, and we have the pull of gravity downward. So these two forces, the two vertical forces, are equal and opposite, so the net force along the y-axis is 0. However, the net force acting on the crate along the x-axis is not 0, so this object is accelerating. So it's not moving right now because I haven't pressed this little start button. I don't know if you can see it. There's a little start button right down here. So when I press it, this object should accelerate across. We have some graphs here that will record the applied force. That's what this little a stands for. This will get us the position, or the acceleration rather, the velocity, and then the position. So let's take a look at this. Notice it's picking up speed, and let's stop it before it hits the wall. Notice the force is 500. If we divide the force by the mass, which happens to be 100 kilograms here, we get an acceleration of 5 meters per second squared. The velocity starts from 0 and increases uniformly. Notice the gradient here is constant. That means the acceleration is constant. If you were to calculate or measure the gradient of this line, what would you get? You should get 5 meters per second squared, because the gradient gives us the acceleration. Here we have a position time graph, and notice that the gradient goes increasing, showing that the velocity is increasing. So the position started out somewhere almost at -10 and ended up at around 8. Alright, so let's double this force now. So it's 500. Let's make it 1500. Triple it. So this acceleration should have changed. It'll change once I press start here. So what do we expect the acceleration now to be? We expect it to be 15 meters per second squared. And so let's take a look at this. The velocity will reset to 0 and start again. So obviously this needs to pick up speed much more quickly now. And well, it crashed into the wall. So this is the force exerted by the wall on this crate. I wanted to stop it before it got there, but this will do. So notice now, let's do this again. And there we go. So notice the acceleration is 15 meters per second squared. Notice this velocity now, the line is a lot steeper, and of course the gradient increases much more quickly. So this line rises and the gradient increases much more quickly, which means the velocity is increasing more quickly, which means the acceleration is greater because the force is greater. So we could change a few parameters here so that we can take into account friction, but we'll do that later on. So I hope this gives you at least an initial idea of what Newton's second law is all about. Let's take a second look at this expression here. Here we have Newton's law expressed in vectorial form. Now this is perfectly okay, but in this course we work pretty much with scalars all the time. So we need to find a way to express this in scalar form, and that's pretty easy. So all we need to say is that the sum of the x scalar components of the force is equal to the mass times the x scalar component of the acceleration. And likewise, we can say that the sum of the y scalar components of the force is equal to the mass times the y scalar component of the acceleration. So let's look at a brief overview of how we're going to solve problems using this law. Say we're given a situation described as we see here. A crate is being dragged across a rough floor by a rope inclined at an angle to the horizontal. The first thing you need to do is identify the forces acting on the crate. So these would be the weight. So remember, the crate's weight is the pull of the earth on it. There would be the reaction, the normal reaction. The floor would be pressing up on that crate. There would be friction, and since it's moving, it's going to be kinetic friction, and we'll talk about this a little bit later on. So just remember, there are two types of friction: static friction and kinetic friction. Static friction is the friction that prevents something from moving. Kinetic friction is the friction that opposes the motion of something that is moving. And then there is the tension. This tension is the force in the rope. So when we analyze problems like these, we use what is called a free body diagram. So I'm going to represent the crate using this dot and these forces by drawing some vectors. So first, let's get our system of reference, our coordinate system here. So obviously this is x, that's y, and then we have these forces. So one force that'll be here will be the weight, then there'll be the tension at some angle. Let's assume it's being dragged to the right. There'll be the normal force. Remember, that's the force the floor exerts upward on the crate, and there is a friction being exerted by the floor but parallel to the floor, and it's kinetic friction, R on top here. And so we apply Newton's laws along these axes. So for along the x-axis we get and when you first write this down, you can simply write all the forces down. So we can just say go counterclockwise and call it Tx. Notice when I'm writing a component, a scalar component, I don't put the little arrow on top. So that's Tx, and so it's plus all the way in x plus f kx plus wx, and then we put the values. So these values, by the way, let's suppose this is at an angle theta to the horizontal. So Tx will be the horizontal component of this. So make sure you understand what I'm doing here. The horizontal component of this force is 0, so I'll just write 0. You could just not put anything, and that would be okay. This obviously would be minus, so I could put plus minus, or I could just take off the plus sign and put minus fk plus the x component of the weight, which is 0. and this is going to be equal to the mass times the x component of the acceleration. So we could rewrite this as by simply saying then that t cosine theta minus fk equal max. And so this would give us one equation. We could label it like, say, label it equation 1. And so I like to label it these little square brackets. So I can refer to this equation by simply saying equation 1. We could do the same thing along the y-axis. And we could say that, well, sum of the y scalar components will be, and we just write this out again. So you always write down all the forces. Later on, as you get better at this, you can maybe skip this step, but don't until you are very sure that you know what you're doing. And right here I forgot to put max rather, so very bad. Anyway, so don't make that mistake. And then we get the values. So obviously now this will be t sine theta, and it's positive because the vertical component points upwards, so make sure you see that. Plus n, that component points upward. The vertical component of this is 0, so we put a 0 there. And the vertical component of this force points downward, so it's minus w, and that's equal to may. Later on you will find out that w can be replaced by the mass times 9.8, and so we could say, instead of w, we could say m times the mass times 9.8, and we'll just call it g to make it easier. It's easier to write g than 9.8, and then that's may. And so this then could be written, we could forget about this and just say t sine theta plus n minus mg equal may, and it gives us a second equation. So very often when we have to solve problems involving forces, we look for two equations and then do some algebra, and that's pretty much it. So I think we've definitely gone over the 10-minute mark. I won't know until I edit this piece. Anyway, so we'll leave Newton's second law for right now, and in the next video we'll look at Newton's third law. Bye for now.